Hello, everybody. My name is Martin. I work for Red Hat at the oVirt project, but today I will not be specifically talking about the oVirt project. I'll be slightly comparing in very low detail, but still I'll be comparing three schedulers. So you will actually learn how we select the host or the node where the VM started when we can start VM button. And I'll show you how OpenStack does that and how Kubernetes does it. So since I have pretty long presentation, without any further delay, first, before we start talking about how the scheduler does things, we need to figure out what the scheduler is actually supposed to do. So what is the goal we are trying to solve here? I mean, the primary goal is easy. Basically, we start a load, or we want to start some load, whether it's container or VM, and we need to find a place for it. But that's only one of the goals. What other things you might want to solve? So, for example, you might want to find a place where the VM will keep running even when something happens. Or if you have containers on it, you need to find a place where the containers will keep running even if one of the VMs dies. So you might not want to start two VMs with the same container on the same host. On the other hand, you might want to make sure that your VM has the highest performance possible if you're mining Bitcoin, for example. Why would you do it in a VM? I have no idea, but you might want to do that. And you might want to keep the power consumption low, for example. So there are many different aspects of scheduling. Starting with VM is just one of them. And all the three schedulers have some specific features that help you with it. So first, before we talk about the schedulers in specific, let's think about what you need to think about when you try to write your own scheduler. Because all the three teams basically have to solve the same set of issues or answer the same set of questions. So first, the size of your cluster. It's actually different if you're trying to schedule a VM and your cluster is 50 hosts or 200 hosts, and if your cluster is 10,000. The algorithms are not going to be the same. You might not care about particular hosts in the 10,000 host scenario, but you definitely care when you only have 10 of them. You need to figure out whether you are going to use probabilistic algorithms or deterministic algorithms. Probabilistic algorithms are really nice, and now AI is all the rage everywhere. Everybody loves artificial intelligence and optimization stuff. But if you want to support your customers, that's not the best approach to take. I mean, if somebody sends you an issue description saying, I've been trying to start this VM and it just wouldn't go to the host I wanted to go to, then you need to somehow debug it. And if all the logic is hidden in a neural net, good luck with that. So all three schedulers are using deterministic algorithms, meaning we have no random function, or almost no random function in there anywhere. So if this comes our way, we'll just simulate the same scenario and we'll see exactly what it's going to do. And we'll see how it's behaving in such a way. The other things you need to answer is, are you going to support migrations or maybe load balancing? It also changes the algorithm slightly. And one of the big questions is, are you going to support homogeneous clusters or heterogeneous clusters? The algorithms get very simple when you only have homogeneous clusters because all are the same size or all have the same memory amount. But when you have heterogeneous clusters, suddenly, comparing two hosts where one has 10 gigabytes of RAM, one has 1 gigabyte of RAM, and they're in a cluster together, becomes much more complicated. Another big question you have to answer is, how are you going to treat your VMs? Is your VM a pet? If you care about, you make sure that it still runs, make everything possible to keep it running, or is it just one cow from your 10,000 cows, and if you just one cow is eaten, you don't really care, you will buy another one, or you will start another one. So that's another big question. Now, scheduler is basically a function. It's the black box in there. So this is how it fits into the environment. All three schedulers I'll be talking about follow the same structure. They're using the same structure. You have a VM. In this case, it's a VM. somebody wants to start a VM. Then you have some configuration that's another input to that function. And you have your set of nodes that's decide. So you have your set of nodes. And all three schedulers, well, all three projects have an agent on that node. The agent is actually the party that does all the work. You tell it to start me a VM, and it does all that's necessary to start a VM or the container. And it doesn't matter if it's called VDSM, kubelet, or whatever OpenStack uses. So you have your nodes. All the nodes, through the agents, are reporting the status and available resources and whatever is running there. And that's the third input to your function. So we have the black box function here. And it really is a function. You have three inputs, and it generates an output. It tells you where you should start the load. Now, the three schedulers we'll be talking about. So I'll be talking about the scheduler using oVirt. I'll be talking about the scheduler that's used in OpenStack. That's part of the Nova project. And I'll be talking about the scheduler that's part of the Kubernetes. There are some differences in the goals there. You can see up in this table. So, for example, oVirt and OpenStack both support low hundreds of processes. That's the official number from documentation. Kubernetes claims to support 5,000. It's a bit more, like 10, more, but it actually didn't affect the algorithm too much. It will still be pretty similar. Now, you see all three are written in completely different languages. Java, Python, Go. I would say that, yeah, they probably had to use something very different. And you see all the load type is different. oVirt has static VMs, OpenStack has static VMs, and Kubernetes has containers. So you see, just when looking at numbers, there are lots of differences between those three schedules. Now, let's talk about how they actually do stuff, and we'll see that even though it looks like they're not really the same, basically all three teams reached almost the same solutions. So first, before we get to the actual algorithm, let's talk about resource planning. That's an important part of the scheduler. It needs to know how much free resources it has on nodes. So let's say we have oVirt. oVirt is data center virtualization. So as I said, we have the management with the scheduler, we have the agent. The agent is on the right side. And currently we have a host with a single VM running. It's occupying some resources. Those are red boxes. And we have a request. That's the arrow that just appeared on the left side. We have a request that just came in. And it's asking, please start with this VM. So what oVirt scheduler does, it basically computes everything, because the resource allocations from the agent, and it computes internally where the VM is supposed to go, and it remembers, if another VM comes in, please remember that there is a VM that's supposed to start. It's not running yet, but I've already reserved the space for it. Those are the small boxes that appeared in the management. Remember that, because that's actually one of the differences in how the three schedulers do things. So then we remember that it's starting, so we tell the agent, please start with VM, and then the agent starts preparing the VM. It takes some time. Starting a VM is not, like this. It can take even seconds if you have to prepare the storage or mount NFS or something. I mean, before the network responds, it can take some time. So during that time, if another request comes in, we remember that there is a VM starting, although it's not there. So we are not double booking resources. And then when the VM actually starts, we'll remove the pending records because we are already getting all the stats from the agent. The agent sees the second VM and it's telling us, hey, there's a second VM running, it's eating memory, it's eating CPU. So we already know the actual consumption. We don't need the pending records. So that's how oVirt does. Now let's look at Kubernetes. Kubernetes behaves differently. Kubernetes behaves differently. So Kubernetes, how many of you are actually using Kubernetes? And how many of you have actually studied the internal architecture of how Kubernetes is is orchestrated internally? A couple of people. So Kubernetes internally has a distributed database. That's the single point of information for everything. So you have etcd, they use etcd, but on top of it there's an API server. That has everything. It's the API endpoint. So when you are trying to start a pod, that's collection of containers. So and that's the workload unit in Kubernetes. You basically send a record, a document describing the pod to the API server. So that's what I'm going to do here. You see, the arrow is actually connected to the API server now, and it created a document that's the light blue one with resource definitions and everything. So it created a document saying, I want this pod to be running. But the API server doesn't do anything. It's really just the information center. So what happens is the scheduler notices, hey, there's a pod, and it doesn't know where to run. And I have all the information, so let's compute the right destination. So here, it's not pushing, the scheduler is actually polling the database. So, I mean, that's a simplification, but scheduler is basically polling the database. So it sees a pod that doesn't know where to run, it takes the information, takes all the information about free resources, computes the proper destination, and writes it back to the API server again. It's not starting anything, it just writes the proper information back to the document with the pod. And then the agent notices, there's a pod, and it's telling me that I should be the one who is running it. So let's do it. And it starts the container, it starts the pod. In this case, we have no pending record because everything is part of the database. Pending means I have a pod that doesn't know where to run, but it already specifies all the resources it needs. So in this case, we don't actually track the intermediate state because we have it in the database. Now, OpenStack does it again slightly different. So in OpenStack, before Newton, it was basically very similar to oVirt. You had a scheduler, you asked it to schedule a VM, it selected the right destination, and it sent the command to it. They didn't have pending, they had issues with double booking resources because it wasn't atomic. OpenStack supports multiple schedulers, as Kubernetes does. So when two schedulers were running at the same time, they were actually stomping on each other's feet. And commonly, the node rejected the VM because the resources were already taken. So they had to retry, and it was expensive. So post-Newton was the current version of Kata, I think. So they introduced a new service. So the service is called placement service. And that's the single point of information for all the resources. So it's again, the request comes to the scheduler asking for a VM to be started. But this time, the scheduler first gets all the free resources from the placement service, asking for data, and then computes the result. But before it starts the VM, it actually sends a reservation request, if you want to call it like that, to the service, to the placement service, and that's atomic. So if some other scheduler already used the resource, the reservation service will reject that request. But if it accepts it, it means that the VM can safely start. So it sends it there, the reservation service says, okay, yeah, that's fine, I'm taking that. And then it sends the request to the agent, and the agent starts the VM. So all the three projects all do it differently. The end goal is the same. You are trying to avoid double resources. It's just that we are collecting data in a different way and reacting on them in a slightly different way. But the difference is actually pretty small if you think about it. Yeah, one project has a placement service, one project has a central database. oVirt supports only one scheduler, so the pending database is inside the scheduler. But that's really a technical detail. So now we have the resource tracking. So the scheduler actually knows how much free resources it has on its nodes. So what's the algorithm? What's the magic? Well, it turns out all three projects follow the completely the same algorithm. It's really the same. even though they are using different language, they support different amounts of nodes. The algorithm is really the same. How many of you remember the topic of map and reduce? It's been, over and over, with Hadoop, and everybody was using it. 5 years ago, 6 years ago, it was all the rage at all the conferences. How many of you have heard about map and reduce? Yeah, it's like almost everybody. So we don't talk about map and reduce, but obviously it's a really cool class of algorithms. We've been doing it like that for years, and it's exactly the same thing, except you have a filter step before it. So everybody follows the simple 3 steps. First, we filter out nodes that are not really able to run the VM or the pod. They don't have enough memory, they miss some hardware, whatever. Then we map the remaining nodes to some number, and then based on that number, we select the best node to use for the VM. All 3 schedulers, and I'll use a simplification again, basically schedule in serial way. When you ask for 10 VMs to be started, they first schedule 1, then the second one, then the third one. There are cases when it's actually parallel, but all these schedulers do it like this, and it's basically serial. So how does it actually work? Let's talk about the filtering. The filtering step is easy. You have some functions, OVirt calls them units, OpenStack and Kubernetes are called differently. I think Kubernetes is predicates, but it's the same thing. Basically, for maintainability purposes, it's a function. And the function takes all the hosts you have at the moment, it takes the load you're trying to start, and it returns a boolean. It tells you, yes, I can start the load based on these conditions, or I can't. So what you are usually checking? You have CPU compatibility. You have free RAM. Those are pretty obvious checks. The VM wouldn't even start. You have network presence or storage. What good is starting a VM if you can't connect to its disk, right? You wouldn't be able to do anything. But there are some others that are not that obvious. All 3 projects support them. Again, with some small differences, but the features are pretty common. So one of them is affinity. All 3 support both VM or pod to host affinity. So you can say this VM or this pod is supposed to run on this subset of hosts. For legal purposes or legal reasons or just because the host supports something you want to use and it's not mandatory for the VM, but if it's there you can use it, or because the host is more powerful or closer to some other host. For example, when you have MySQL and web service, you would probably want the VMs and web services, the web server and the database to run together closer, so you are limiting latency. So basically, we have affinity. And as I said, all 3 support both pod to a host affinity or interpod affinity. So you can specify pretty complex rules, especially in Kubernetes. Kubernetes combined with labels, which I have there in bold because it's a really important topic. In Kubernetes, you basically have a fully expressive language where you can express complicated rules with logical formulas and ors that will declare that this host is good for this pod or it's not. The other important topic that is related to what I just said is load isolation. For example, OpenStack is a special filter that allows you to say that this customer's VMs, if you, for example, have a shared hosting with 4 VMs, these customer VMs are never going to be mixed up with VMs from another customer. Or these VMs are processing payment data, so they never will run on a host that has a web server on it, just because of meltdown, for example. That's a really cool thing that appeared. It's a And this is exactly what you would use to mitigate a virtualized environment apart from kernel freezes. So you will never mix up VMs in safe and unsafe areas. And again, you would use some affinity or you would use some isolation logic. All three projects support it. So scoring is a bit more complicated. So, yes?
Was the stimulus for negative affinity?
Yeah, so, the question is if we have support for negative affinity. I'm pretty sure Kubernetes has, oVirt has as well. I don't remember if OpenStack allows you to express that. I think it does. But it's just, out of my head, I'm not really 100% sure. Yes. Yeah. So you can specify a rule that says this VM will never run on this host. Or these two VMs will never run together, which is important for the case I explained at the beginning. Basically, when you have Kubernetes cluster on top of oVirt, for example, and you are using VMs as nodes for Kubernetes, and you have a container that's highly available, it has multiple copies, but if those copies are running in a VM, or in VMs, multiple VMs, and those VMs are on the same node, it's not highly available, right? So you can use negative affinity between those VMs to actually put them to separate physical nodes, and that way you are highly available. So yes, you can use negative affinity as well. What we don't have, at least in oVirt, is inverted affinity. Run anywhere except this node, or something like that. So, but we have negative affinity. Now back to scoring. Scoring is tricky. If you have just one metric, for example, free memory, it might look like an easy job. You will just select the host that has the most amount of free memory. But what if the goal is not to spread the load evenly? And that's kind of an oVirt specialty. We actually support multiple different policies, and one of them is power saving. So you might actually put as many VMs as possible on as few hosts as possible, just to save power. During the night, all employees go home. Some VMs are still running, but let's put them together and shut down all the other hosts. And then in the morning, let's change it to evenly balanced again, so before they come to work, all the other hosts or some of the other hosts will boot up again, and they'll spread out the VMs. That actually saves power, and it can, how the expenses for data center are spread out across different payments, basically. Usually 50% of your energy budget for a data center is cooling. So if your VMs are not running and the hosts are not running, you are saving lots of money. Seriously, lots of money. So that's one of the goals. You can have power saving policies. And in that case, scoring becomes different. But now, we don't have just memory. Let's say we have memory and CPU. And which one of those is more important? Is free memory more important or CPU load more important? Yeah, you can't really tell. I mean, it's the customer's decision what's more important, and that's why you have to deal with that. Now, what I wanted to talk about here as well is that how we represent the numbers. CPU, it can be percents of CPU load, right? So think about heterogeneous cluster. I mean, all your machines are using a different CPU. So let's say you have Core 2 Duo, which is a pretty old processor, and i7 in the same data center. 10% of the CPU is going to be totally different performance. So you can't really tell which one is the highest performance. So you could use GPs or time slices or whatever. Everybody's using percents, but technically for CPU, it's not as obvious as it looks like. For memory, you could use percents, but all your loads are usually using fixed numbers. You do not specify the amount of memory for a VM as 10% of the host. You will say 4 gigabytes, which means it kind of doesn't make sense to use percents for memory tracking. You use absolute numbers. Now, label presents, if you have soft affinity, meaning I would like the VM to run add a host with this label, but it doesn't have to if it's not possible. That's basically booting 0 and 1. So it's actually not as easy. You have to think about how to represent the numbers. Yeah. So now let's back to selecting the destination. Which node is the best one? I already touched it. So basically, you have to let the user specify some multipliers. You say CPU is 10 times as important as memory, or the other way around. So I have that. All three projects support that. oVirt has a UI for that, so you can change it dynamically. For OpenStack and Kubernetes, you have to change the configuration file. But it's basically the same thing. You just say CPU function is multiplied by 10. But still, you get some numbers, and now you have to actually select the best one. So you have a score of 10 for CPU, 2 for memory, or 2 gigabytes for memory. But how do you sum up 10% of CPU load plus 40 gigabytes of free RAM and booting for label? Well, you need some normalization to get them so they are comparable. And I have a table here. So the normalization algorithm is actually different in all three projects. Each project decided to use a different function. They're doing it the same way, it's just that they use different maximums and different functions. So for example, oVirt uses RAM. We sort all results from the CPU function and assign score based on how many hosts are worse than you. So if you have 3, one has 10% of CPU load, the other 2 have 20, the first one will get score 3. OpenStack uses dynamic maximum. Basically, all the hosts that go to filtering and get to scoring will take the maximum amount of memory there. So if you have hosts with 4, 2, and 1 gigabytes, the maximum is 4 gigabytes, and then they scale everything based on the maximum of all the hosts. So they'll use percentage. They normalize to 0 to 1 in floats. Kubernetes is a bit special. It's like they want to use homogeneous clusters only because they use the maximum of the single host. So every host has a different scale. They use just how much memory there is on a single host when they normalize the free memory. So it's basically 50% of the available memory on this host and 25% of the other host. If the memory sizes or the amounts of physical memory those hosts are different, the numbers are not really comparable. But that's basically what you have. There are some disadvantages to all three algorithms. For example, the oVirt algorithm compresses the differences. If you have a huge difference or small difference between the next neighbors after sorting, the difference in score is just 1. But it still works really well. Nobody's complaining. So another topic I was mentioning is balancing. So there are multiple different methods, and here the projects really are different. oVirt supports we have pet VMs, so we support live migrations. We'll do whatever we can to keep the VM running. So if the host gets overloaded, we'll migrate the VM somewhere else. So that's live migration. OpenStack supports live migration only when the sysadmin clicks a button or does some action. They don't automatically migrate and Kubernetes, obviously with containers, currently have no migration at all. Except when the logic decides to start up another version of the container and then maybe shut down some other. So it's basically, you can achieve offline migration. Start second container and kill the first one. So there's an offline migration. As I said, especially for there are situations that appear during runtime, you can have hosts can become overloaded over time. I mean, the VMs were doing nothing, your employees were doing nothing basically, and then one day somebody starts a 3D modeling software in there and some rendering, and suddenly the host that was hosting 20 VMs that are mostly sharing everything becomes overloaded. So oVirt will try to distribute the load. In OpenStack and Kubernetes, if you have something like that, you have to solve it somehow. I'll show you another way of doing that on the next slide. Well, let's talk about balancing for a second. basically what you need to do is you need to select a candidate, like a VM or pod, you want to do something, and then the action. And that's hard. I mean, doing it completely properly for balancing can be a complete problem. So we have over some very simple algorithms. We basically have two thresholds, and we have overloaded, underloaded. For equal balance, we'll just be moving load from overloaded to underloaded. So all VMs are all hosts are in the middle group. For power saving, it's the same thing. Just underloaded. I mean, hosts we can actually shut down theoretically. They'll move all the VMs from there to the middle group. And overloaded is the same. I mean, we move VMs from overloaded to the middle group. So we are not doing any artificial intelligence. There is no magic right now. For Kubernetes, they have something called preemption. It's pretty new. So they can decide that something that has higher score is more important, it's about to start, and we don't have a place for it. So they basically use what's called disruption budget of other pods to ask for a place. Can you please stop one of your copies so I can use the place for something that's more important? But it's not asking that nicely, but you get the idea. Basically, each pod specifies, or the group of pods specifies, how willing it is to give up this space for the sake of the cluster. And that's a different approach because containers are slightly different than VMs. Now, Amazon Web Services, the spot instances is the same thing, except you don't have score, you have money. So you say how much work is your load? How much work is your load? And if the current price is higher, Amazon will just kill your VM to start the load that earns them more money. So that is the same thing, it's preemption. Now, good ideas and highlights. Some stuff I didn't talk about. oVirt actually has a component that uses techniques from artificial intelligence or optimization techniques. It's called oVirt Optimizer, and it's an oVirt tool for system needs. We actually run computationally intensive algorithms to see how we can balance your cluster. We will never execute, currently we'll never execute it automatically. We'll just tell the admin, hey, if you want to have better performance, please move this VM there and this VM there, and it will be very balanced. Or you can't start this VM right away, but if you first move VM A to host B, then suddenly you have enough space. So we have a tool like that. But it's an optional tool, and it's only helping you. OpenStack has a chance scheduler. You can just decide, oh, what the hell, I'm going to try whatever host I have, and if it works, I'll use it. If it doesn't, I'll try again. Kubernetes has arbitrary logic. I already talked about that. You can actually express complicated logical formulas to specify the rules for where a VM or pod can start or not. Now, PCI pass-through is another topic that's too complicated for this talk. It took more than an hour when I did the rehearsal, and I had to cut it in half, basically. So you can pass through devices, graphical cards, SRIOV stuff, VNX, and in oVirt, you are tied to a host. In OpenStack, the sysadmin in advance prepares a list of labels, and basically it says this device from host A, this device from host B, and this device from host 3 are the same function. And then you just ask for a function, and the scheduler knows that there are 3 different hosts with the necessary capability. And then on the Kubernetes side, I really like the reactive and declarative way of doing things. I mean, there's a central database and everything is happening there. Everybody pushes in and somehow modifies the object. That's really cool. It's a really good idea. So let's get back to good ideas, because we are getting out of time, unfortunately. So labels. I mean, the way Kubernetes uses labels is just awesome. You can do almost anything with them, except countable resources, and they have a different mechanism for that. So basically, all the filters OpenStack has, or almost all the filters OpenStack has and oVirt has, we could just replace them by labels. Sysadmin will prepare some rule that will label the host accordingly, and it will be done. The scheduler will do whatever it needs to do, and it's all labels. Then normalization methods, they're really important because they behave, they control how the cluster behaves in terms of which host is the best one. And I had pretty nice comparison of all three with nice tables and numbers. I had to remove it. But if you want to talk about that, I'm here all day, actually all weekend, so just find me around. And then the most important part of everything is atomic resource tracking and reservation. I mean, you really can't have a scheduler without that. You can't have resources. Depending on what you need, you have multiple schedulers, speed rate protections, and balancing and preemption. We've discussed that, but those depend on what you actually need for your use case. So summary, I'll really shorten it up. There are really ideas that are worth sharing across the schedulers. Each has some really nice points that it's using, and none of them is the best one. We can really work together and share what we've learned over the years using them. And the differences are pretty small, actually. So thanks. I think I'm out of time. So that was it. So if you have any questions, you can ask questions. Yeah, sure.
Is there any way to scheduler?
I couldn't hear you properly.
That way you put everything into a single scheduler?
Yeah, if we can put everything into a single scheduler. Well, technically, why not? There are some differences, as I said. Kubernetes tries to support 5,000 nodes. So, for example, what they do is when they compute memory and CPU load, there is just a simple function that puts those two together and divides by 2. That was really hilarious find in the code because OpenStack and oVirt and them separate. But they just do it in very simple ways so they can compute lots of scheduling runs as fast as possible. The same with normalization. They basically have no normalization per host. So we could, but sometimes we go somewhere not exactly the same. Any other questions? Well, if you've seen our presentation at the beginning of the day, it was actually talking about starting VMs and Kubernetes cluster.